Good morning, students. Mr. Carver here. Today we're going to be doing section 1.4. 1.4 is one-sided limits. And then before we're out of here today, we'll talk about continuity. So essentially, one-sided limits are nice because you work them exactly like you work two-sided limits. So let's say I have something like this. Let's say the limit as x approaches 2. And you'll know it's a one-sided limit. You've got a little sign. It's kind of up in the air there. And that negative means from the negative side or the left side. So we're going to be thinking about numbers like 1.99, 1.99999. And then, of course, if I've got the limit as x approaches 2 with a plus sign, all that means is from the positive side or the right-hand side of the number line. So numbers like 2.001, 2.0001. Now, the nice thing about two-sided limits is you work them exactly like you work one-sided limits, like I said before. So let's just say I've got something like that. The very first thing you do is you're going to take that value of c and you're going to plug it in. That gives me 4 minus 4 on the top and 2 minus 2 on the bottom, which is indeterminate, which means we need to do more to it. So what we're going to do is we're going to factor x plus 2, x minus 2, all over x minus 2. Factoring and canceling is one of our techniques. And then I just take positive 2 and I just plug it in, which gives me a limit of 4. And it doesn't matter if it's from the left or from the right. You do exactly the same thing. So now if I'm coming in from the right-hand side, I just take and I plug it into my reduced form, and I get 4. So work them exactly the same as you did before. Here's another quick example. Let's say I take the limit as x approaches pi over 6 from the left of the cotangent of 5x. And you guys love this because it's trig, and it goes right back to the thing I had you memorize the first day of class. You take this value of c and you plug it right there. This is really the cotangent then of 5 pi over 6, which we know is the flip of the tangent of 30. Tangent of 30 is 1 over root 3. So this is going to be the positive square root of 3 over 1. And I'm in Q2, and the tangent and cotangent are both negative there. That's your answer. So again, two-sided limits work exactly like one-sided limits. Now, there are some differences, all right? And here's the main difference. One-sided limits. They can be infinite. And we'll get into that in section 1.5, but two-sided limits cannot be infinite. Easy for me to say, but one-sided limits can. It's very, very important. It's not going to impact you tonight in section 1.4, but it'll be coming soon, so we'll talk about that next week. Let's do one more example here. Let's say I take the limit as x goes to, let's do 4 from the left, and I've got the square root of x minus 2 all over x minus 4. Again, the first thing you always do is just plug in that value of c. That gives me 0 over 0, which is indeterminate. And we already know, since we've got a radical in the top and the bottom, in the top, and a difference, I'm going to multiply by the conjugate. This gives me root x plus 2 on the top and the bottom, keep in mind. So if I FOIL out the top, again, I'm still taking the limit as x approaches 4 from the left. FOIL at the top, I'm going to get x minus 4. You can use the box and prove that to yourself. And on the bottom, I get x minus 4 times root x plus 2. Now, don't FOIL at the bottom because you're looking for cancellations. And what you'll notice here is those do cancel. I got a 1 on the top, and now I can just plug in 4 into there, and I get root 4 plus 2, otherwise known as 1 over 2 plus 2, which is 1/4. And that is my limit. All right, now we're going to be dealing with piecewise functions. Let's just say that I've got the limit, f of x, And it looks something like this, x squared plus 2x if x is less than negative 1. Let's do 2 if x is negative 1. And let's do 5x plus 6 if x is greater than negative 1. And what if I said, hey, take the limit, and you could pause this anytime if I'm going too quickly. Let's go negative 1 from the left of f of x. All right, so what you're going to do then is you're going to pay attention to these instructions here. This tells you when to use which of those equations. If I'm coming into negative 1 from the left, I'm talking about numbers that are smaller than negative 1, which means I'm going to use this line right there. And again, the first thing you do to evaluate a limit is take negative 1 and plug it directly in there. It gives me negative 1 squared plus 2 times negative 1. That is 1 take away 2. The answer is negative 1. Now let's take the limit as x approaches negative 1 from the right. So now instead of doing the top, I'm talking about numbers that are just slightly larger than negative 1, so I'm going to use the bottom. Whoops. Of f of x. This is going to give me 5 times negative 1 plus 6. What? That's a 5. There's a 6. And that gives me positive 1. All right, so just pay attention to the piecewise instructions. Now let's talk about continuity. So basically, a function is continuous if you can trace it without lifting your pencil. So let's say I've got a graph that looks something like this. Nice and continuous all the way across. So those are all, that is a continuous function. What they call a discontinuous function might look something like, as you might imagine, something with a vertical asymptote in it, where I actually have to lift my pencil. Something with a hole in it, which causes me to lift my pencil. So let's separate these out. And then maybe one last picture, something that looks maybe like a piecewise that makes me have to lift my pencil. So continuous on top, discontinuous on the bottom. To prove continuity, I'm going to have you show me that certain conditions exist. And I want you to show the following. Number one, that f of c exists. By the way, let me back up here just a little bit. This is continuity at x equals some number, like 5, 15, 28, something like that. I'll tell you what that value of c is. So you just want to show that a dot exists. And I'm going to walk through how to do all of this stuff. But first, let's just get this list down. So there has to be a dot. Secondly, the limit as x approaches c of f of x must also exist. Add this to your notes. They have to be matching finite values for a two-sided limit. So what you're looking for is that the two sides actually come together at the same y value for this value of c right there. And then lastly, to make sure that it's continuous, you need to show that the dot equals where the two sides come together. So f of c equals the limit as x approaches c of f of x. So what you need to do is show that the left-hand side comes together at the right-hand side, that's step 2, but that they actually come together at that dot right there, making it continuous. So you need to show all three of these conditions. All right, so let me walk you through a couple of examples to show you what I'm looking for tonight's homework. Let's say that I've got f of x is equal to, let's do x squared plus 3x if x is less than negative 1. And let's do 5x plus 3 if x is greater than or equal to negative 1. All right, and I'm looking to see if this is continuous at x equals negative 1. So again, here's what we're going to do. First of all, I have to show that f of negative 1 exists. Does it? Sure. This second line here says that if x is equal to negative 1, you use that function right there. So that's 5 times negative 1 plus 3. I believe that gives us negative 2. So check. I got a dot at negative 1, negative 2. So that's a good sign. Step 2, I'm going to take the limit as x approaches negative 1 from the right of f of x, and let's go ahead and do that right now. So if I come in from the right-hand side, I'm still using the bottom one there. That gives me negative 2, because I just plug it directly in. And now I want to take the limit as x approaches negative 1 from the left. Now instead of using this bottom one here, I'm going to be using this top one here, because I'm less than negative 1. So if I now plug in negative 1 wherever I see an x, this gives me positive 1 plus a negative 3. That gives me negative 2. So check. Both of these are finite and matching values. So this is looking really good. Step 3 here then. All you have to do is tell me that f of negative 1 equals the limit as x approaches c of f of x. You can literally write it just like that, because we know that f of negative 1 is negative 2, and the limit is negative 2. So step 1 and step 2 are the same number, and we are good to go. So this is continuous. All right, let's look at another example. Let's do this one. How about f of x is equal to, let's do 3x squared plus 6 if x is greater than 1. Let's do 5 if x is 1. And let's do 9x if x is less than 1. So I'm looking for continuity at x equals 1. That's my c value. So step 1, f of 1. Well, I'm going to use this middle one here. So my answer is 5. So check. I got a dot at 1, 5. Step 2, let's take the limit as x approaches 1 from the right. And let's do the limit as x approaches 1 from the left. Let's see what we have here. So if I come in from the right, I think I'm going to use this last one here. No, I'm not. I'm going to use this top one. So I'm coming in from the right, slightly bigger than 1. I take a 1, I plug it in there. That looks like I'm going to get 9. All right, let's come into, rather from the left-hand side, and it looks like I'm going to now use the bottom one here. So I plug 1 in there, and that also gives me 9. So check. I got a limit. These are matching finite values. However, step 3, you can see that f of 1 is not equal to the limit as x approaches 1 of f of x. So this is not continuous at x equals 1. So let's think about what's happening here. Look, you've got two sides coming together at 9, and you got a dot at 5. So it looks something like this. Two sides come together at 9, but I got a dot at 5. So it looks like a piecewise. It looks something like that. I have no idea actually what they look like individually, but that's certainly possible. This is 1 along the x-axis. All right, so it's not continuous, but I'd like you to put this last rule in your notes. If a function is discontinuous at x equals c, but the limit exists, step 2 is true, then the discontinuity is said to be removable. So if a function is discontinuous, it fails the continuity proof, but step 2 is true, step 2 works, the discontinuity is said to be removable. So if I look at this previous example, it is not continuous, but step 2 works. So this is a removable discontinuity. Now, another word from a removable discontinuity is nothing more than a hole. So step 2 says the two sides come together at the same y value, but there's a discontinuity somewhere right at that dot. That either means that there is a dot somewhere else or there is no dot at all. That is a removable discontinuity. Non-removable. Discontinuities would be vertical asymptotes or jumps in the graph. All right, people. I think that should be enough to get you through tonight. I do have the homework posted to my website. Talk with you soon.